Solving topological formation tasks of Swarmbot systems that employ mobile Sbots. Swarmbot systems that employ intelligent mobile Sbots enjoy a wide range of applications in the modern day, often related to reducing risk to human life. Some of these include protecting territories externally and internally, supporting power structures in physically disorganized environments, search and rescue operations, and assistance in the agricultural sector. These Sbots are noted for their particular advantages compared to other Swarmbot systems, such as having tunable structures and programmable logic, the ability to reconfigurate, having more resistance to failure as a result of these properties, and increasing the radius of action and the set of tasks with a growing number of Sbots included. The problem studied in this paper is the situation where there's an unforeseen change in a physically disorganized environment. In this case, the Sbots have to rebuild their parameters and function stably. The new unforeseen circumstance might require solving a new problem, such as overcoming new unknown obstacles. This calls for a built-in algorithm that is applied in this situation, which includes mechanisms for forming various topologies by the Sbots. In order to program the Sbots so that new topologies are formed, we propose that they're formed corresponding to the shape of the new obstacles, and we propose the use of the theory of Poya's enumeration for this solution. To use Poya's theories of enumeration requires setting up a graph theory method that comes with its own necessary axioms for fulfillment. Some of these are closure, associativity, presence of neutral elements, and inverse elements. The full detail of the method is described in the paper, and the results are as follows. We're taking 3 intelligent mobile Sbots in a Swarmbot system. 4 topologies are possible. Each of these is different with the relational status of the Sbots to the others. You have one Sbot system where all of the Sbots are equal, and as a result there's no parameter b. In another case, you might have one Sbot which is equal to another, while that other has a higher status than a third, giving a single-edge graph. You might have a two-edge graph system where one Sbot is higher in status than another, and one that is higher than another, or indeed one Sbot that's higher than 2 other Sbots, but which are otherwise equal, giving a more complicated 3-edge graph. The paper also explores cyclical structures that arise as a result of the possible Sbot combinations and relational statuses, and the table summarizes the findings. The paper shows how different topologies can be formed by the Sbots by the use of different status relationships like equal or 2 higher than 1, 1 higher than 2, and so on. And the authors convinced themselves that the use of Poya's enumeration theory allows forming new topology that correlates with the shapes of new obstacles. Further investigations into this topic could do comparative analysis with other Swarmbot system algorithms and seek to eliminate the disadvantages associated with Sbot systems, such as low speed of detection and low speed of location of ground target points.